Good morning, quantum enthusiasts. Welcome back. Today it's a great day because we're going to be doing one of the two most famous algorithms in all of quantum computing, Grover's algorithm for SAT. So we'll get back to the stuff written on the left side of the board later at some SAT instances that you might think about, but we'll come to that later. Great. So before we dive into it, it's not a very complicated algorithm, but there's some stuff going on. So before we dive into it, I want to talk a little bit about kind of a geometric lemma, like a little mini geometric programming problem, and do it at the beginning, even though it's maybe not that motivated, just because we're going to need it later. We want to put it in our pocket so we don't get sidetracked. We're in the middle of Grover's algorithm. So this little geometric programming problem is about a kind of unitary operation. The unitary operation that's reflection across a vector. Now, normally, you most often think of a reflection as there's a mirror, which is like a plane, and you reflect things in the mirror. And that's true. You can have reflections through a plane. But this is a slightly different thing. It's reflections across a vector. So what you should imagine is you have some vector v in space, and think of it as I wish I had the last prize pantry, which had a poster tube. It would have been perfect for this. But imagine a long, thin tube that's made out of a mirror, and things get reflected through it. So if this is the mirror, this vector gets reflected back here. This vector gets reflected up here, and so forth. So somehow, if this is the vector v, anything that's what happens actually is that v itself doesn't change. V gets fixed, but anything that's perpendicular to v, lying in this plane down here. It's a bit hard to draw. That's perpendicular to v. It gets negated. So it goes to here. I don't know if I drew that very accurately. Okay. So another way to put it, recall that we always can remember this fact that every unitary breaks down into a bunch of 2D planes where it does rotations, and 1D lines where it does negations, and 1D lines where it does nothing. So how does this particular one break down? So it has no 2D planes of rotation. There's no rotation going on in this thing. So no 2D rotation planes. And it has one axis or one direction where it does nothing. Call it one axis of no op, which is v itself. Okay, that stays fixed. Or if you really love linear algebra, this is an eigenvector with eigenvalue 1. But I'll just call it the direction in which nothing happens. And then all the other directions get negated. Okay, so if it really is a 3D picture like this, then you can also think of it as it does a 180-degree rotation in this plane. That's what it means for both dimensions here to get negated. But in higher dimensions, it's not really a rotation. It's just it's basically the negation operation, except in the direction v. Okay, so that's the geometric aspects of it. But let's see an example of it. I guess I'll erase. Oh, it's right down here. What's an example operation of this type? I'll do an example in 2 to the n dimensions. It's this operation. If b1 or b2 or ... or bn, then minus. Okay, so this is a quantum operation that we could kind of easily code up. Why can we easily code it up? Well, it's not hard to code up classical and or not code for oring together n variables. And then we have this black box machine in our mind that turns classical and or not code into this sort of if that then minus operation. Okay, so this is something we can easily code up with I don't know, order n, maybe 2n instructions. And how does this particular code operate? Well, if you think about what it does to vectors, so this maps all zeros, the basic state of all zeros, well, the OR is not true, so it just stays itself. So it stays 0, ... 0. And on the other hand, if you have some other bit string, like x1, x2, ... xn, and x is not the all zeros string, well, then the OR of these bits is 1, so you do minus, so this gets minused. Okay, and this is exactly like the story here, where this axis of unchanging is the all zeros string, and the other dimensions all getting negated is this. Okay, so this is maybe like the name that, I don't know, we would first think of for this operation. But I'm just trying to tell you, you could also call this instruction reflection across the basic state all zeros. So I'll write that here. You could also call this reflection across the vector of all zeros. Or, as I said before, you could maybe equally well describe it in words using this as your way of thinking about it. So you could also say this is, if perpendicular to all zeros, then minus. Okay, so these are, these expressions in quotation marks are like two maybe geometric ways to think about this quantum operation. And the main thing I want you to remember is like this quantum operation is easy to program. And so we can program this kind of geometric operation ourselves. Okay, I'll even write that here. It's easy to program. I think it's like around 2n instructions. Okay, any questions about this? So let's try to generalize this a little bit. This is about coding up reflection across this particular vector, the basic state all zeros, or the extremely tall vector with a 1 in the first coordinate and zeros everywhere else. What if you want to reflect across some other vector? Could you do that also easily? Okay, so let's ask this as a question. The answer is going to be often yes. So is it easy to code this thing, reflection across V? Or I'll write it in a different way. If perpendicular to V, then minus. These are the same things. Well, I should add for other V's. Let's say unit vector V's. And the answer is yes, if you have code for creating V itself. So yes, if you can easily create V. Okay, I mean, if V is just some crazy vector that you don't know anything about, it's not going to be easy to code up this instruction. But conversely, if it's a normal vector and you know how to build it, then it's not too hard. So let's see why that's true. First, what do I mean by you can easily create this vector V? So imagine you have some code where, like, okay, the first line of code is like new qubit b1 through bn. Always going to be imagining we have n qubits, or 2 to the n dimensions. And then you have like a block of code. And at the end of the block of code, the new state is of these n qubits is V. Okay, so some block of code. And this block of code, if you compress it all together, think of it as like one composite operation. It's a unitary operation in 2 to the n dimensions. So this whole thing corresponds to some real unitary transformation, u, that's 2 to the n by 2 to the n. Okay, so what I'm assuming here in trying to answer this question is that, okay, we have some code that we know how to do that basically makes a unitary, some kind of space rotation that produces v. More particularly, that takes the state here, which is, ket all zeros, and turns it into v. So just to rewrite this assumption, I'm assuming that you have this block of code. It's hard to erase. Corresponding to a unitary u, such that if you apply u to this vector, which is like the basic state you start with when you initialize n qubits, you get v. And conversely, and this is like a fun aspect of quantum, you could run this code backwards and replace each instruction by its own undo. And actually, most of our instructions are their own undo. So you could run the undo of this code. And therefore, you could say that, conversely, the all zeros, ket all zeros, is what you get by applying like the undo of u to v. Okay, if you remember like our homework, okay, mathematically, this is usually called u inverse. And if you remember homework, since it's also a unitary matrix, it's the same as u dagger or u conjugate transpose. But I'll just write the undo of u. Okay, so what I want to tell you is we're trying to figure out, can we do this operation, if perpendicular to v, then minus. And we know that we can do if perpendicular to all zeros, then minus. Moreover, we know this like kind of rotation of space u that takes zeros to v and vice versa. So can somebody suggest how to, putting these facts together, how to make this? Yeah. I think what you said is correct. Yeah. So I'll write it. So in order to do this instruction, it's 3 steps. 1, let me write it and then I'll say it. Undo u, which basically means run this block of code backwards. And then 2, you do this instruction. This is like if b1 or b2 or ... or bn, then minus. We know how to do that. So we do this instruction, which I'll use by this name, if perpendicular to all zeros, then minus. And then we do u. We just do u. In other words, we run this block of code forwards. Okay, so why is this? Like, imagine this is v. We want to reflect. We want like a subroutine that reflects across v. So what we want to first do is like rotate our world so that v becomes the all zeros vector. Then we want to do reflection across the all zeros vector, which we know how to do. And then we want to like rotate our world back so like all zeros goes back to being v. And that's geometrically what we want to accomplish. This is basically like, we just want to like turn our heads in the space so that, the all zeros direction becomes the v direction becomes the all zeros direction. Okay, so maybe just writing some comments on this code, if you will. The point is that this rotates, space, if you will, bringing, in particular, ket v to this special vector, the all zeros vector, that we're good at. That's what this line says. And then this accomplishes reflection through the all zeros vector. Check. This reflects across all zeros. Okay, and this just rotates space back so that things are back to normal. So all zeros, the thing we just reflected to, goes back to V. Okay. Any questions about this?
That's where it's
Yeah, good. If V is one of this is particularly easy, good. If V is one of the basic states, it's pretty easy. So let's say V were, n was 3 and V were 1, 0, 1. You always do know what V is. V is like fixed in your mind. Like I know what V is. I can like write this code and like hypothetically analyze, what state it creates. In fact, like you have a state in mind, and you write some code, like you have some code that can generate it. Now, in this case, like a different way to do it is like it's kind of similar. This is very similar to this. Probably here you want to say this would be like if B not B1 or B2 or not B3, then minus, I think. Because this instruction, which we can code because we know classical code for doing this, so we can make classical code for this. This instruction leaves this one the same, and like every other direction it negates. So what I'm showing you here is that like if V is a state that you yourself know how to create with code, so it's kind of like an easy to get a handle on state. Like you're like V is not like some bizarre state. Like it's a state that I can like code up myself. Then you can also make the operation that reflects through that V. And maybe it's a good life thing to remember as well, which is you're trying to decide, hey, can I like program this geometric transformation with quantum code? If all the aspects of it are like kind of simple, then you should be able to do it. Like it's not super crazy. It's like a reflection. And like this random vector V is not some bizarre vector that we know nothing about, but like I have some code that can make this vector. So you're like, this should like inspire you to think like there should be some way to implement reflection across V. And indeed, like this is the code that does it.